Okay, so you're tuning in probably because you're, neck deep in DevOps, Kubernetes, cloud stuff, maybe prepping for an interview, or just really want to get what makes modern software tick.
Yeah,
Well, either way, you're definitely in the right spot. Think of this as like your fast track. We're cutting through the noise to get to the good stuff.
exactly. And we've got some really practical material today. It's a set of DevOps interview questions, but not just questions, detailed answers too.
Wow, so real world stuff.
Totally. These are the kinds of things people actually get asked.
Mm.
So understanding them, well, it gives you a real leg up on what's important and how it all connects.
Right. So our mission today, pretty simple. Dissect these questions, pull out the core ideas, the practical uses, and hopefully give you that solid understanding without, drowning you in jargon. We want those aha moments.
Definitely aiming for those.
We'll be hitting Kubernetes basics, Terraform for infrastructure, some key Docker commands. It should be, informative, maybe even a bit fun.
And it's grounded.
Yep.
Not just theory. We've got actual YAML examples for Kubernetes,
Yeah.
a Terraform script for spinning up a VM.
Yep.
Those Docker commands you'll actually use. It's all practical.
Perfect. All right, let's just dive right in then. Kicking off with Kubernetes fundamentals. The pod. What is a pod, fundamentally?
Okay, so the pod. It's basically the smallest deployable unit in Kubernetes, like the absolute basic building block.
Smallest unit. Got it.
Think of it as a single running instance of your application process. But here's the thing. A pod can actually hold more than one container.
Oh, great.
Yeah, if they're tightly coupled, need to share resources like storage or networking, they live and die together in the pod.
Okay, so a logical group. And we have this pod.yaml example. What's this telling Cube?
Right, so this YAML file, YAML, by the way, that's just a human-friendly format. Cube uses a lot, defines a pod named Nginx pod.
Okay.
Under spec, you see containers. Here, just one, named Jinx. And the image is also in Jinx. So pull the standard Nginx image.
From Docker Hub or somewhere?
Usual, yeah. And it says the container listens on port 80, standard HTTP. So basically it's telling Kubernetes, hey, run one instance of Nginx for me.
One pod, one Nginx container, port 80. Simple enough. But what if Nginx gets super popular? One instance isn't going to cut it. That's deployments, right?
Exactly. That's where deployments step in. Think of a deployment as managing the pods. Its main job is making sure you have the number of identical pods you want the replicas running.
So if one crashes,
the deployment controller notices and spins up a new one.
Yay.
It maintains that desired state. Plus, it handles updates, rolling updates, rollbacks, all that good stuff to minimize downtime.
Okay.
And technically, deployments often manage something called replica sets underneath. The replica set really makes sure the right number of pods exist. The deployment is more like the manager overseeing the strategy, including updates.
Gotcha. Strategy manager versus the enforcer. And there's a deployment.yaml example too.
Yeah.
How's this different from the pod YAML?
Key difference right away.
Yeah.
Spect.replicas.
3. 3 pods.
That's exactly. Tells Kubernetes we want 3 identical Nginx pods. Then you see a selector and a template.
Right.
The template is the blueprint for the pods, basically the same Nginx container definition we saw before. The selector is how the deployment finds the pods it manages using labels. Here it's looking for app.nginx.
Okay.
So the deployment says, keep 3 pods matching app.nginx running using this template.
Yeah.
If not, fix it. It's all about the desired state reconciliation.
Makes sense. Desired state. Okay, so deployments keep the right number of pods running, handle updates. But how do we reach these pods? From outside or even other parts of the system? That's services, I assume?
You got it. Pods come and go, right? Their IPs can change. So you need something stable. That's what Kubernetes services provide, a stable IP address, maybe a DNS name for a group of pods.
And the source mentions 4 types.
Yep. Cluster IP, node port, load balancer, and external name.
Okay, let's break this down. Cluster IP first. When do you use that?
Cluster IP is the default. It gives the service an IP address that's only reachable inside the cluster.
Internal only.
Right, perfect for microservices talking to each other. Your front-end pod needs to call a back-end API pod. Use a cluster IP service. Keeps internal traffic internal.
Okay, contained within the cluster. Makes sense. What about node port?
Node port exposes the service on a specific port on each of your cluster's nodes. It's the same port number across all node IPs.
So you can hit any node IP on that port.
Exactly. You might use it for like testing, maybe, or if you're on-prem and don't have a fancy cloud load balancer. But for cloud production, you'd usually go with load balancer type. Just be aware node port uses a specific port range.
Got it. Access via the node's IP. Next up, load balancer. Sounds like cloud.
Totally. This type hooks into your cloud provider's load balancer, AWS ELB, Google Cloud Load Balancer, Azure's. When you create one, Kubernetes talks to the Cloud API, provisions an external IP, and sets up the load balancer to send traffic to your pods.
Ah, the standard way to get stuff onto the internet from the cloud.
Pretty much, yeah. Gives you scalability, high availability. Just remember, it usually costs extra from your cloud provider.
Right, makes sense. And the last one, external name. Sounds different.
It is quite different. It doesn't point to pods inside your cluster. Instead, it acts like a DNS alias within the cluster that points to an external DNS name.
Like pointing to an external database service.
Exactly. Instead of hard-coding my database.amazonoz.com everywhere in your app configs, you create an external name service, like my DB service inside Kubernetes that points to it. Then your apps just talk to my DB service.
Ah, indirection. Nice.
Yeah, makes configuration easier. The cluster's DNS just resolves it to the real external name.
Interesting. Okay, services covered. The questions then pivot to infrastructure as code, specifically Terraform. Big topic. What's the main idea there?
Terraform is all about managing your infrastructure. VMs, networks, databases, you name it, using code. Instead of clicking around in a console.
Which gets old fast and is error-prone.
Right. You write declarative configuration files saying what you want. Terraform reads that and figures out how to make it happen with the cloud provider API.
So benefits are?
Huge benefits. Version control for your infra. Repeatability, spin up identical environments easily. Automation reduces errors, speeds things up. And Terraform keeps track of what it built in the state file.
State file, right.
Yeah, so it knows what needs to change if you update the code. It aims for idempotency, running the same code multiple times, gives the same result. Really powerful.
And we've got a simple Terraform script here. AWS EC2 instance. Can you walk us through this? Provider, resource, AMI, instance type.
Sure. So provider Oz tells Terraform we're talking to AWS in the S East 1 region here. The provider is the plugin for that specific platform.
Okay.
Then resource Oz instance example. This defines the actual thing we want in AWS EC2 instance. Oz instance is the resource type. Example is just our local name for it in the code.
Got it.
Inside, AMI instance specifies the Amazon machine image. That's the template with the OS and stuff.
Like Ubuntu or Amazon Linux.
Exactly. Instance type T2.micro sets the VM size. T2.micro is small, good for testing, and tags just adds metadata like a name tag. So run this. Terraform talks to AWS, builds the specific VM.
Like a recipe for infrastructure. Cool. Okay, next, back to Kubernetes networking. The difference between port, target port, and node port. These definitely confuse people.
It can be tricky. Let's try that hotel analogy again.
Okay.
Node port is like the specific numbered door on the outside of the hotel building. The node, say, door 380. Traffic comes in there.
Right, from outside the cluster.
That traffic gets routed internally to the service's own port, its internal listening post. That's the port defined in the service YAML. Maybe that's port 80. But the service needs to send that traffic to the actual application inside the pod. The application might be listening on a different port, say port 8080, that's the target port.
Ah, so they don't have to match.
Nope. Node port, external entry on node. Del port, service internal port. Door port, pod container port.
Hotel analogy works. Okay, sticking with external access, load balancer, node port. But Ingress comes up again as more advanced. What's the deal with Ingress?
So load balancer and node port usually expose one service per external IP or node port combo. It can get messy and expensive with load balancers if you have many services.
Right.
Ingress is smarter. It acts as a single entry point for HTTP and HTTPS traffic, and it can route requests to different backend services based on the URL host name or path.
Like mydomain.com, my B goes here, mydomain.com web goes there.
Exactly. All through one external IP usually. But you need an Ingress controller running in your cluster. The Ingress resource is just the set of rules.
The configuration.
Yeah, the Ingress controller is the actual engine, like Ingix or Trafic, that reads those rules and manages the traffic flow, often configuring an underlying load balancer that allows fancy routing, TLS termination, often more cost-effective.
Smart traffic cop for web apps. Got it. Okay, shifting gears. Helm, the package manager for Kubernetes. Is that a good way to think of it?
It's a great way to think of it. Perfect analogy. Deploying a Kubernetes app often means juggling multiple YAML files, deployments, services, config maps.
Yeah, it can be a lot.
Helm packages. All those related Kubernetes manifests into one thing called a Helm chart.
So the chart is the package.
Exactly. It's got the YAMLs plus templating so you can customize configs when you install it. And these charts can live in Helm repositories like app stores for Kube apps.
Okay.
When you install a chart, Helm creates a release that's your specific deployed instance of the chart with your settings. Helm tracks releases, makes upgrades and rollbacks way easier. It really tames the complexity.
Sounds like it. Okay, Docker time. Expo in the Dockerfile versus Docker run now at P. What's the real difference? Always confuses me.
Yeah, common confusion. Think of expos in the Dockerfile as just documentation. It signals which port the app inside the container intends to listen on.
A hint?
Pretty much. It tells humans and other tools, hey, port 8080 is probably important here. But crucially, it does not actually publish that port to the host machine. That's what Docker Run He does. The Docker Run He flag creates the actual mapping between a port on your host computer and a port inside the running container.
The connection.
Exactly. Expose 80 just says, I'll use 80 internally. Docker Run P 8080.8i says, map port 8080 on my host to port 80 inside this container. You need the AOP to actually connect from the outside.
Documentation versus connection. Okay, makes sense now. And this command, Docker run 80d at 80d to 80, 80.8do in Jinx lurky, break it down.
Sure. Docker run. Well, that starts a container.
Right.
GG means detached mode. Run in the background, give my terminal back.
Handy.
And DP 80.80 is that port mapping. Map host port 80 to container port 80. Since Nginx listens on 80 by default, this exposes it directly on the host's port 80.
Okay.
And Jinx at the end is the image name. Docker will pull it from Docker Hub if you don't have it locally, then start the container from it.
Simple, powerful command. Okay, quick network protocols recap. HTTP versus HTTPS, TCP versus UDP. The essentials.
Right. HTTP hypertext transfer protocol, basic web traffic like fetching web pages.
Yeah.
Unencrypted, usually port 80. HTTPS, the S is for secure. Same thing, but encrypted using SSL/TLS. Protects the data, usually port 443. Essential these days.
Definitely. And TCP UDP.
Those are lower level transport protocols. TCP transmission control protocol. It's connection oriented, reliable, make sure all data packets arrive in order. Think HTTP, SSH, email, rely on this.
The reliable one.
Yeah. UDP, user datagram protocol. Connectionless, it's faster, sends packets without checking if they arrive or in what order, less overhead.
So faster, but maybe loses stuff.
Exactly. Good for things where speed matters more than perfect reliability, like DNS lookups, video streaming, online games. Trade-offs?
Secured versus unsecured, reliable versus fast. Got it.
No. Docker files again. What is a Docker file really?
It's just a text file, but it contains instructions line by line telling Docker how to build an image. It's the recipe, the blueprint for your container image.
Step-by-step instructions.
Yep. Each instruction usually creates a new layer in the image.
And we've got a Node.js example from workdir, copy, run, CMD, common instructions. What do they do? Okay. From Node.14, that sets the base image. We're starting with the official Node.js version 14 image.
It's a foundation.
Right. Workdir app sets the working directory inside the image, like cd app. All subsequent commands run from there.
Makes sense.
Copy package.json copies your Node.js dependency files, package.json, package-lock.json, into that app directory.
Okay.
run npm install executes that command inside the image during the build. It downloads all the Node dependencies defined in package.json.
Installs the libraries.
Exactly. Then copy copies the rest of your application code into app.
All the JS files and stuff.
Yep. And finally, cmd node, app.js. This defines the default command to run when someone starts a container from this image. Here, it runs node app.js, starting the app.
The command that launches the application.
Got it.
And base images, what are they precisely? And what are typical ones for Python or Node?
The base image is just what you put in that from line. It's the starting point. Provides the basic OS, maybe some core libraries. Choosing a good one matters for size and security. For Python, you typically use python.something, like Python.bot 3.9 or maybe Python 3.9 Slimbuster for a smaller Debian-based image.
Slim is smaller.
Usually, yeah. For Node.js, like we saw, Node.something, Node or Node.16 Alpine. Alpine Linux is super tiny, very popular for base images. Using official ones is generally a good idea.
Start with a trusted base. Makes sense. Okay, next. Checking open ports on Linux. Vital skill. How do we do that?
Oh yeah, essential for troubleshooting and security. The source lists 3 common ways: netstat tom, sstoln, and lsoff.
Okay.
Netstat tom is the classic. Shows listening TCP, UDPU, doesn't resolve names and shows listening sockets.
lstoln.
Else is newer, often faster, does basically the same thing. Socket statistics, same flags, give similar output.
And lsoff.
lsoff means list open files. With LAPN, it shows network files, numerically, without name resolution. Then you pipe it to grep. Listen to only see the ports that are actively waiting for connections.
So different tools, similar goal, see what's listening.
Exactly. Super useful to check if your service started correctly or if something unexpected is running.
Definitely. Now, firewalls, obvious perhaps, but what are the core benefits?
Yeah, seem obvious, but good to state clearly. Main job. Control network traffic based on rules. Block unwanted incoming connections.
Keep the bad guys out.
Basically, yeah. Protect internal systems and data from unauthorized access, various network attacks. They also let you monitor traffic, see what's going on. It's just a fundamental security layer. Isolates your trusted network from untrusted ones like the internet.
Critical gatekeepers. Okay, we mentioned Ingress before. This question drills down on the Ingress resource versus the Ingress controller. Nail that distinction for us.
Right. The Ingress resource is the Kubernetes object. It's YAML. It's where you define the rules. Like request for host.myapp.com path.ap should go to the AP service.
The configuration file.
Exactly. The Ingress controller is the actual piece of software running in your cluster. It could be Nginx, Traefik, a proxy, or a cloud provider's implementation. It reads those Ingress resources.
Writes the rules.
And then actually implements them. It configures the underlying proxy or load balancer to make that routing happen. So Ingress resource declares the intent, controller makes it reality.
Yeah.
You need both.
Declaration and execution. Clear. Okay, Kubernetes controllers again. Deployment, StatefulSet, ReplicaSet, DaemonSet. We know deployments are for stateless apps, updates. What about StatefulSets? When do you need those?
StatefulSets are for, well, stateful applications. Things that need stable, unique network identifiers for each pod and persistent storage that sticks with that identity.
Like databases.
Databases are the classic example. PostgreSQL, MySQL, Cassandra. Also things like message queues, Kafka, Zookeeper. They need that stable host name. Pod 0, Pod 1, guaranteed ordering for startup and shutdown, and dedicated persistent volumes. Deployments just treat pods like interchangeable cattle. StatefulSets treat them like named pets.
Cattle versus pets. Good analogy. Okay, so StatefulSets for stateful apps. ReplicaSet, we touched on this. It's lower level than deployment.
Exactly. ReplicaSet has one simple job. Make sure X number of identical pod replicas are running. That's it.
Just maintains the count.
Yep. You tell it, I want 3 replicas, and make sure there are 3. Deployments actually use ReplicaSets under the hood. When you update a deployment, it creates a new ReplicaSet with the updated POS template, scales it up, and scales the old ReplicaSet down.
Ah, so deployment orchestrates the update using replica sets.
Precisely. ReplicaSet is the basic building block for ensuring replica counts. Deployment adds the update strategy on top for stateless apps.
Got it. And DaemonSet. Sounds different again.
Totally different goal. A DaemonSet ensures that one copy of a specific pod runs on every node in your cluster, or a specified subset of nodes.
One per node. Why?
For things you need running on every machine. Think log collectors, like Fluent or Logstash agents, or monitoring agents, like Prometheus Node Exporter, maybe cluster networking components. These are node-level infrastructure services. DaemonSet guarantees they're present everywhere.
Makes total sense for those kinds of agents. Okay, probes next. Liveness, readiness, startup. Keeping apps healthy in Kube, right?
Exactly. Kubernetes needs ways to ask your application, are you okay? Why does probe, are you alive? If this probe fails, Kubernetes assumes the container is deadlocked or broken and restarts it.
Okay, restart if unresponsive. Readiness.
Readiness probe. Are you ready to serve traffic? If this fails, Kubernetes knows the container is running, but maybe it's still initializing or overloaded, so it stops sending new traffic to that pod until the probe passes again.
So alive, but not ready for work yet.
Right. Doesn't restart it, just takes it out of the service load balancing pool temporarily.
Yeah.
And startup probes.
Startup for slow starters.
Exactly. Some apps take a while to initialize. Startup probes tell Kubernetes to wait longer initially before starting the regular liveness readiness checks.
Yeah.
It gives the app time to get fully up without being killed prematurely by a failing liveness probe.
Liveness, breathing, readiness, ready for work, startup. Still warming up. Got it. Okay, back to stateful versus stateless apps. We mentioned databases for stateful. More examples.
Sure. Stateless, things that don't need to remember anything between requests. A web server serving static HTML. An API endpoint that just does a calculation based on input. Each request is independent.
Forgets immediately.
Right. Stateful needs to remember things. Databases, obviously. Shopping carts on an e-commerce site. The server has to remember what's in your cart. Online game servers tracking player state. Anything where persisted data or session information is key.
Remembers and persists. Clear. Now, namespaces. How do they help organize a busy cluster?
Namespaces are like virtual clusters inside your physical cluster. They let you partition resources. Super useful if you have multiple teams or different environments like dev, staging, prod, all sharing the same Kubernetes cluster.
So Team A can have a web app deployment in their namespace.
And Team B can have a completely different web app deployment in their namespace, no name collision. Namespaces provide that scope. Plus, you can set resource quotas, CPU memory limits, network policies, and access controls per namespace.
Like dividers in a shared office, management and isolation. Good. Last question area, port forwarding. When and why?
Kubectl port forward. Oh, super useful for development and debugging. It lets you connect directly from your local machine to a specific port on a pod running inside the cluster.
Bypassing services.
Yeah, it creates a direct tunnel. Say your pod is running a web server on port 80, but it's not exposed externally. You can run a kubectl port forward my pod name 8080.80.
Okay.
That command forwards traffic from port 8080 on your local machine straight to port 80 on my pod name inside the cluster. Then you just open localhost port 8080 in your browser to hit the pod directly.
Ah, a direct line for testing. Lifesaver sometimes, I bet.
Definitely. Great for accessing internal dashboards or debugging tricky issues without setting up full services or Ingress.
Awesome. Well, we really have covered a lot of ground there, diving into those interview questions, Kubernetes building blocks, services, controllers, Terraform, Docker basics, networking, Helm.
Yeah, and seeing those practical examples, the YAML, the Terraform code, the Docker commands, really helps connect the dots between the concepts and, actually doing things. It builds a solid foundation.
Absolutely. So, for everyone listening, here's something to chew on. Now that you've got a clearer picture of Kubernetes controllers deployment for stateless, StatefulSet for stateful, ReplicaSet for counts, DaemonSet for node-level stuff, think about some specific applications you know. Which controller would be the best fit, and why? Really considering those characteristics helps lock in the understanding.
That's a great exercise. And maybe the next step is exploring Ingress controllers more deeply or checking out the huge library of Helm charts out there. There's always more to learn, right? This deep dive hopefully gives you that confidence to explore further.
Definitely. Thanks for joining us on this deep dive. Until next time, keep learning, keep building.